So in previous class we have discussed the use of elastic constant and the significance of elastic constant, why elastic constant are very signify for to calculating the relation between stress and strain, or to calculate strain theoretically. Now it is also very interesting to see how they are related to each other. What is the relation between elastic constant? So in today's class basically we will discuss the relation between elastic constant. Okay. So first relation is relation between modulus of elasticity, bulk modulus and Poisson ratio, right? That is also known as generalized Hooke's law. So this is the relation between E, K and mu. Okay. Okay. So in today's class we will discuss how they are related to each other, basically how E, K, mu are related to each other. To derive this relation we are considering a cubical element, right? It is a cubical element and subjected to hydrostatic state of stress, or you can say the volumetric state of stress, or you can say spherical state of stress, right? Just like I am considering a cubical block and these are the coordinate system x, y, z, and in all three direction it is subjected to the stresses that is called sigma x in x direction, sigma y in y direction, sigma z in z direction. And now we are interested to see how much strain induced in all three direction due to these triaxial state of stress. If the stress is same in all the direction, the triaxial state become volumetric state of stress or hydrostatic state of stress. The meaning, in the previous class we have also discussed that volumetric stress. The meaning of volumetric stress, if the stress acting in all three direction is same, that stress is called volumetric stress, right? But if the stress is acting in all three direction is the different, or you can say the load is acting in all three direction is the different, the stress is called triaxial state of stress. So this figure is basically representing triaxial state of stress. Triaxial state of stress. If in this diagram sigma x is equal to sigma y is equal to sigma z, then this diagram will represent the volumetric state of stress, or you can say hydrostatic state of stress, because if we are hydrostatic of state of stress means we are considering volumetric stress is equal to the pressure, because the intensity of the pressure is same in all the direction. So now we are interested to calculate, due to this triaxial state of stress, how much strain induced in all three direction, because these are the normal stresses. So the strain induced is also the normal strain. So it is difficult to view or difficult to consider if I am considering simultaneously the three stresses acting over the body and to calculate how much strain induced in the x direction. It is very difficult to understand. So that's why for simplification I am considering the case number 1, if the stress is acting only in x direction. If stress is acting only in x direction only. If the stress is acting only in x direction, the meaning of that, what is the meaning of that? This is the cubical element we are considering to prove the relation. If the stress is acting only in x direction, only the sigma x is acting over the body. If the stress sigma x is acting over the body, how much strain induced in the x direction? The question is that. What is the strain, what is the value of strain induced in the x direction, right? And we have already studied that what is the longitudinal strain, what is the lateral strain. As we have discussed in the case of longitudinal strain, when the load is acting in any direction, in the direction of the load, the change, whatever the change taken place, that come under the category of longitudinal strain. So also we have seen that if we are considering it is the case, this figure is representing, if the stress is acting only in one direction, how we can represent it? Uniaxial state of stress. This figure is representing uniaxial state of stress. And in case of uniaxial state of stress, we are interested to calculate how much strain induced in x direction, how much strain induced in y direction, and how much strain induced in z direction. Because it is a three-dimensional body, if I applied force in any direction, the change will taken place in all the direction. In the direction of the load, change is longitudinal, and in other direction, the change is known as the lateral. So load is acting in one direction, but the strain induced in all three directions due to that load, right? One direction change called longitudinal strain, and other direction change will be called lateral strain. And we have also seen that this relation we have also seen in the previous class. In case of uniaxial state of stress, if any member is subjected to the uniaxial state of stress, and we have seen the stress is directly proportional to the strain, and this stress is nothing else, that is the E times strain. So what is the value of strain in that case? That is the longitudinal strain, sigma by E. So what is the value of longitudinal strain due to the uniaxial state of stress? That is sigma by E. And in that case, how much is the stress acting? Sigma x. So what is the value of this? Sigma x, and E is the modulus of elasticity. And what is the value of strain induced in the y direction? In x direction, the strain is longitudinal, and in y direction, the strain is lateral. And what is the value of lateral strain? We have also seen in previous lecture that lateral strain is directly proportional to the longitudinal strain, and lateral strain is equal to, we have also seen this, lateral strain is directly proportional to the longitudinal strain. And if we remove this proportionality sign, so that lateral strain is equal to mu times longitudinal strain. And we always consider with negative sign, because longitudinal and lateral strain always in opposite sense, opposite direction, right? So we always consider a negative sign. So we are interested to calculate the lateral strain, and what is the lateral strain here is epsilon y, that is minus mu times what is the longitudinal strain is epsilon x. And what is the value of epsilon x? Sigma x by E. So simply we can write here minus mu times sigma x by E. Similarly, we can write strain in y direction, that is also the lateral strain, and what is the lateral strain? Minus mu times longitudinal strain, and what is the longitudinal strain? Sigma x by E. So minus k mu sigma x by E. The load is acting only in x direction, the stress induced, normal stress induced in the x direction is sigma x, right? And due to that load, due to that stress, we are able to see strain induced in all the three directions, because stress and strain are the tensor quantity. Any quantity is said to be tensor quantity if it has more than one direction. Scalar does not have any direction, or zero order vector. Vector, or you can say having one direction, or you can say first order vector. Stress and strain are the second order vector, which having more than one direction is known as the stress, because the force is acting only in one direction and the strain produced in all three directions. Similarly, this way we can write case 2. If the stress is acting only in y direction, what happened if the stress is acting only in y direction? What is the meaning of that? If we are considering case number 2, in case number 2, we are assuming that the stress is acting only in y direction, sigma y. That is the x direction, that is y direction, that is z direction. If the stress is acting only in y direction, so how much stress induced in y direction? Longitudinal strain. And how much strain induced in other two direction? Lateral strain. So similar way in similar fashion I can write like this. How much strain induced in y direction, because the strain induced in y direction will be the longitudinal strain, because we are applying force, we are applying stress in y direction. In which direction we are applying the force, the strain induced is known as the longitudinal strain, right? So what is the value of longitudinal strain here? That is the sigma y over E, just from this relation. Now the force is acting in y direction, so the stress induced in the y direction, and due to that stress, how much strain induced in the y direction? Longitudinal. And what is the value of that longitudinal strain? Is sigma y over E. And what is the strain in lateral dimension? That will be minus k mu times sigma y over E. And what is this figure is representing? Figure is representing uniaxial state of stress, because only the uniaxial state of stress. Similarly, we can write, I am not case 3. What is the case 3? If the stress is acting only in z direction. This is the x direction, y direction, and this is z direction. Suppose I am considering another color so that easily we are able to differentiate. If the stress is acting in z direction, sigma z is acting only. This figure is again representing uniaxial state of stress. Now the force or stress is, why I am saying again force? If we know the force, we know the stress, because just we have to divide by the area, cross section area, because it is a normal load. If we divide by the cross section area, we will get the normal stress. So that's why every time I am calling, that is also I am calling load as well as stress. If the load is acting only in z direction or the stress is acting only in z direction, the strain induced in the z direction, what is the value of strain induced in the z direction? That will be the longitudinal strain. And what is the value of longitudinal strain? Sigma z over E. And what are the strain induced in x and y direction? That will be the lateral strain minus mu times sigma z over E. So these are the 3 different cases we have considered. By considering uniaxial state of stress, we have seen how much strain induced in all 3 directions. If we are combining all these 3 cases, this is the case number 1, this is the case number 2, this is the case number 3. If we are combining all these 3 cases, what will happen? We will get this figure. We will get this figure, that is the triaxial state of stress. We will get this figure. That is the triaxial state of stress. If we combine this together, the figure will be like this, triaxial state of stress. So if we are combining all these 3 equations, this is the equation number 1 suppose, and this is the equation number 2, and this is the equation number 3. If we combine all 3 equations, so we can calculate how much net strain in x direction. In this case, now we are combining all 3 cases. When we will combine all 3 cases, the case will be like this, triaxial state of stress. In that case, we are interested to know how much strain induced in the x direction due to the triaxial state of stress, because this is the case now. So we can see sigma x by E here, and what is the epsilon x is here, minus mu times sigma y by E, and what is here, minus mu times sigma z by E. So simply I can write that is sigma x over E minus mu times sigma y over E and minus k mu times sigma z over E. Right. So this much is the strain induced in the x direction due to the triaxial state of stress. This much. Yes. This much is the strain induced in the x direction due to the triaxial state of stress. Similar fashion, we can write how much strain in y direction. In similar fashion, we can write how we are writing basically. In which direction we are writing? We are writing the longitudinal. In other two direction, we are writing the lateral. Longitudinal, lateral, lateral. We are writing in x direction, so we have written in x direction longitudinal, in other two direction lateral. So in similar fashion, we can write sigma y over E minus mu times sigma z over E minus mu times sigma x over E. Because we are writing in y direction, so we are considering in y direction is the longitudinal strain, in other two direction is the lateral strain. In similar fashion, we can write strain in z direction. In z, we will write the longitudinal strain, that is the sigma zy. In other two direction, we will write the lateral minus sigma y over E minus mu times sigma x over E. So these are the strain induced in x direction, y direction, in z direction. Now we are interested to see how much strain induced, how much volumetric strain induced. So what is the value of volumetric strain? How we will calculate volumetric strain? So the volumetric strain is nothing else, strain induced in x direction plus strain induced in y direction plus strain induced in z direction. If we combine total strain in all three directions, then we will get the volumetric strain. If we are interested to calculate how much volume change taken place due to the triaxial state of stress, so simply we can write the volumetric strain is nothing else, that is the ratio of change in volume to the original volume. Original volume of cubical element we know, and strain we have calculated by using these formula, and simply we can calculate how much change in volume taken place due to the triaxial state of stress, right? So we can combine these if we are writing this. So what is the formula that will be? So we can see from this formula here, right? We can see here sigma xye, and two others times also sigma x is coming. This is sigma xye minus k mu times, means if I combining all, so the formula becomes sigma x plus sigma y plus sigma z. I have taken common ye. One time it is coming and minus 2 times it is coming with mu. So that will be the epsilon b. This way we can get, because in single terms we are getting 1 times, in mu times we are, with mu terms we are getting 2 times. So that wise 1 minus 2 mu. I have taken the common sigma x plus sigma y plus sigma z by e, and 1 minus 2 mu become the factor if I combine all these three equations, right? Now if I am considering the volumetric stress, when will be the triaxial stress become volumetric stress? When I will say the stress in all the direction is same, that is equal to the volumetric stress. Till now the case we have considered is the triaxial state of stress, means the stress acting in all three direction is the different. Now I am interested to know how much stress, how much strain induced in all three direction due to the volumetric stress, due to the hydrostatic state of stress, due to the volumetric stress, hydrostatic stress, and also known as the spherical state of stress. There are three different names we can call: volumetric, hydrostatic, and spherical state of stress. What is the meaning of that? When the stress is same in all three direction. If stress is same in all three direction, so the stress induced is known as the volumetric stress. So in that case, in case of volumetric stress, we can see here, if I put here, so that will be the epsilon b equal to the 3 times sigma b over e 1 minus 2 mu. That is the formula. And also we know that we have also seen the relation between volumetric stress and volumetric strain. We have developed with the help of bulk modulus. What is that relation? So we have seen volumetric stress is directly proportional to the volumetric strain, and volumetric strain is equal to k times this volumetric stress, k times volumetric strain. If we put this formula here by using k, so we can put here, right, in case this epsilon, in place of epsilon b, what we can put? Epsilon b is equal to sigma b over k. We can put this formula here. So if we put this formula, sigma b by k is equal to 3 sigma b by e 1 minus 2 mu. What will we get? we will get the formula and the value of this sigma b cancel out to each other. This will become E is equal to 3k 1 minus 2 mu. That is the relation between E, K and mu. So, what is the relation we have developed here? E is equal to 3k 1 minus 2. That is the relation between E, K and mu, and also known as the generalized Hooke's law, right? It is very useful to calculate some formula based problem, to solve the formula based problem. Sometimes we know two constant and interested to know the third constant, right? So, this way we can derive the generalized Hooke's law. Okay, I hope it is clear to everyone. Now, the second relation we are going to develop here, relation between E, G and mu. Relation between E, G and mu. Modulus of elasticity, modulus of rigidity and Poisson ratio, right? So, to develop the relation, these we are considering, you can say we are considering a just like a rectangular plate, or you can say the square plate, just like this suppose, and that square plate we are considering the under the case of pure shear, means pure shear. If we are considering a square plate, right, or a square block that is under pure shear, the meaning of pure shear, only the shear stress acting over it. There is no normal stress acting over it. Because here we are developing the relation, we are using a constant G, and G come into the picture when we are talking about the shear stress. Okay. In last case, we are interested in K, and K come into the picture when we will talk about the volumetric stress. So, that is why the last derivation based on the volumetric stress, and this derivation is based on the shear stress. So, to understand this derivation, we have to consider a square block, and that square block is under pure shear. Under the action of the pure shear or under the action of the load, what will happen with this? It will distort. There is a angular deformation. How it will angular deform? Under the action of the shear load. If I am talking about load, that is the meaning of stress, because just we have to divide by the area. If we divide the surface area, suppose in place of tau I am saying the shear force F is acting, if just divide by the plane surface area, then we will get the shear stress. So, how it will distort? So, it will distort like this. Under the action of the pure shear, this will distort like this, like this, like this, like this, like this. Due to the tangential load, the final position will be like this, and suppose this is the diagonal, and this will be the diagonal, like this. This will be the diagonal in the same line. Suppose this is the initial position A, B, C, D. The final position becomes C dash, D dash, and this is, suppose this point is representing here E. So, that is E point. And how much deform? This side, suppose this is deforming 5 by 2, and this side it is deforming 5 by 2. So, that is the deformation is plus minus 5 by 2. That is the angular deformation. If any square plate or a square block is subject under the pure shear, how this block will deform like this, plus minus 5 by 2. If I am considering the shear angle is 5 by 2 from one side, so the deformation will be plus minus, angular deformation will be plus minus 5 by 2. So, we can also derive this relation by using this block, but it is very difficult to understand. For the convenience sake, I just fix the lower block. I just fix the lower face of this block. I am considering a square block and fixing the lower face of this block, only the convenience sake, so that we are easily able to derive it. Otherwise, if we derive from this, it become very complicated, right? But it will be deformed like this. Under the action of the pure shear, the block will be deformed like this, right? But for the convenience sake, we are fixing the lower face of this block. If we are fixing the lower weight on the upper face, if we are applying the shear force, the body will distort like this. The angular deformation is, now we are considering it is a phi. Right? The initial position is A, B, C, D. Right? The initial position is A, B, C, D. After the application of the force, what is the position? A, B, C dash, D dash. And initially the diagonal is AC and final position of the diagonal become A, C dash. So we have to consider, right? So we are fixing the lower face of the block and we will get angular deformation like this. Okay? And we can also visualize here. Something we can visualize, but we can visualize here. If you observe here, the block AC, initially the diagonal position is AC. After the application of the tangential force, the diagonal become AC dash. Initially AC and the final position is AC dash. So we can see, we can compare both the diagonal. The length of diagonal will increase. If the length of the diagonal increase, it means that is under tensile force. It means whenever we are applying the shear load on any block, there is a plane which is as 45 degree under pure normal load, because the length of the diagonal is increasing and there is a possibility of increasement of the length due to the normal load. How the length of any member, any block will increase? Whenever we are applying the normal load. If the load is normal, the length of the object will be increased. Length will increase if the load is tensile load. Right? So it means if any member is under pure shear, so one diagonal is subjected to the tensile stress. Due to that, the diagonal change to the final position AC to AC dash. Correct? Another diagonal, if we observe another diagonal, it was the initial position BD. After the application of the tangential force, the position become BD dash. Now this diagonal is shortened. What is the meaning of that? The diagonal contract. Simple meaning is that any compressive normal force is acting over that diagonal. When the length of this specimen or this object will decrease, when we apply the compressive force. If we compress from both sides, then there is a possibility of the shorten of the length. It means one diagonal which is at 45 degree is subjected to the tensile normal load. Another diagonal which is at 135 degree or perpendicular to the another diagonal is subjected to compressive normal load. I hope it is clear to everyone. So we can conclude from here. Also there is a derivation regarding that. If any member is under pure shear, there are two plane. One plane, there are two perpendicular plane. One is at 45 degree, another is at 135 degree, subjected to the normal stresses. Subjected to the normal stresses. One is tensile normal stress and another one is the compressive normal stress. Okay, I hope this geometry is clear to everyone, why we are considering this geometry, why we are fixing this lower face of this block, only the convenience sake. So that simply we are able to derive the relation and simply we are able to understand. Okay, so I am going to derive this. So for that I need space, so I have to clean this and I will derive this by considering this figure. So initially I am interested to see how much strain induced in the diagonal AC after the application of the load, after the tangential load, how much strain induced in diagonal AC. So I am interested to see how much strain induced in the diagonal AC. And which strain is inducing in the diagonal AC? Normal strain. Because the length is increasing, means the dimension is changing. And we have also discussed already, if the dimension change take place, it means that is the normal strain. Load is tangential. Surprisingly, see it. Load is tangential, load is shear, but the strain induced in the diagonal is normal strain because the length is increasing. When the length will increase, what will happen? There is only one possibility, the dimension is changing. There is only one possibility, the load is acting as normal load. So that's why the strain is normal strain. And how we calculate the normal strain? The final length of the diagonal become AC dash. Initial it is AC divided by original length, that is AC. This much is the normal strain induced in the diagonal AC. What is this? Change in dimension to the original dimension. Initially the length is AC. After the application of the shear load, the length become AC dash. We have to do some little bit geometry also. We draw the perpendicular from the point C. We just draw the perpendicular over the line AC dash, and we are calling this point is E, right? So that, and we are also considering this, after the application of the force, whatever the deformation taken place, that is very small, and we can consider these are the arc. CC dash and DD dash are the arc, because when the change will taken place, the angular deformation, it will represented by the arc. Okay, or we can consider these arc are just like a straight line, and this angle is almost equal to the 45, because the change is very small. When we are considering this phi is very small, so we can consider this angle is almost the angle of the diagonal of any square, that is equal to the 45 degree, right? So what we can write this AC dash minus AC from this geometry, because we have draw this perpendicular, so this AC become AE. When this AC become AE, because we draw the perpendicular over this line AC dash, so we can write it EC dash, EC dash over AC. What is this EC dash? What we can write here EC dash? From this triangle, so from this triangle ECC dash, we can write cos 45. So what is the value of cos 45? This CC dash upon EC dash. So we can write CC dash cos 45, CC dash cos 45 divided by AC. Which geometry we have considered for this? For this we have considered triangle CEC dash. In this triangle we have taken cos 45, and cos 45 is nothing else, that is equal to EC dash by CC dash. So EC dash, what is the value of EC dash? We have put here. And what is the AC? Because it is a square, so AC is equal to BC. And what is the value of EC? We can write in terms of, if we are taking tan phi from here, so tan phi is equal to, in this triangle BCC dash, if we are taking tan phi, CC dash over BC, right? If phi is very small, as I am saying, phi is very small. If the phi is very small, so tan phi can be written as a phi. So the phi will be CC dash over BC. And this BC is also equal to AB, because it is a square. Because we are considering a square block, and the sides of the square is same. So we can write BC is equal to AB. So we can also put these value here. So what is the value? We can say here, we can easily put in place of AC, that is the value is equal to CC dash over AC. In place of AC, okay, suppose we are taking this angle, this is the 45, okay. If we are considering this, we have to mention our AC, we are converting, we are taking the sine 45 here, sine 45. In this triangle we are considering sine 45, that will be BC upon, in this triangle ACB we are considering sine 45, so that will be BC upon AC. So what is the value of AC here? BC upon sine 45. And we can put this value here in place of here AC. In place of AC we can put this. So this value become CC dash over BC, and this become Sine 45 and cos 45 both having the value of 1 by under root 2. So we can say cos 45 into sine 45. And this value CC dash upon BC, what we can write? Phi. So what is the relation come here? That will be the phi upon 1 by under root 2 into 1 by under root 2. That will become phi by 2. Okay, I hope it is clear. So how much strain induced in the diagonal AC? Normal strain how much induced? That is equal to the phi by 2. And we also know phi is nothing else, that is known as the shear angle, and shear angle is also known as the shear strain. We have also seen that, because shear strain is nothing else, that is the shear angle. So we can write gamma by 2, that is equal to the how much strain induced in the diagonal AC. And we have also seen from the modulus of rigidity relation, modulus of shear stress is directly proportional to the shear strain, and shear stress is equal to G times shear strain. And what is the value of strain here? Tau by G, and we can put this value here. So how much is the strain induced in the diagonal AC? We can put here, that is the tau by 2G. That is the first part of this derivation. That is the equation number 1. I hope it is clear from the geometry. The simple concept is that we are interested to calculate how much normal, because we have seen the length of the diagonal is increasing. So if the length is increasing, so definitely the load is acting is the normal load. So the stress is normal stress. So the strain is also the normal strain. And we are interested to know how much strain induced in the diagonal AC. And this much is the value of the strain induced in the diagonal AC. For the second part, we are considering when any member is under pure shear. I have already mentioned, whenever any member is under pure shear, there are two planes. Suppose this is the reference plane. Any plane we are consider can be reference plane. If we are considering two planes, one is at 45 degree and another is at perpendicular to that, or you can say from here 135 degree. When any member is under pure shear, only the shear force is acting over the member. There are two planes, one is at 45 degree, another is at 135 degree, subjected to the only normal stresses. One is tensile stress along one diagonal is, or along one plane is tensile stress, and another plane is compressive stress. And the magnitude of these stresses are equal to the value of shear stress. It can be also proved. So I am not interested here to develop the relation for the pure shear case. I am only interested to know that how much stress induced in diagonal AC and how much stress induced along the diagonal BD. And we can also understand from this geometry also. One diagonal is length is increasing, another diagonal length is shortened. Length increased due to the tensile, length shortened due to the compressive. So there are two planes, one is at tensile load, another one is at the compressive load in case of pure shear, and these planes are at 45 and at 135 degree. So if I draw the diagram for that, so we can also draw, it means this diagonal AC and this diagonal BD, these are subjected to the tensile stress. The meaning of tensile stress is length is increasing, and this is subjected to the compressive stress. The meaning of compressive stress is length is shortened, and the magnitude of this stress are the same as the shear stress. That is, there is a derivation for that, you can also reference that from any book, but we are here not interested to develop the relation for pure shear case. We are interested to develop the relation between the elastic constant. That's why I am not going in that side. So the magnitude is equal to the shear stress. Okay. So now you can see this figure is representing the y-axial state of stress. Only there are two directions the stresses are acting. Suppose, okay, there is some confusion, maybe the confusion. If I rotate this figure 45 degree, if I rotate this figure 45 degree like this, Now the figure is like, the stress is here tau, the stress is here tau. I just rotated 45 degree here. This is tau, this is tau. What is this case? This is the y-axial state of stress. We have seen in the last, when we have discussed the volumetric stress, we have seen that triaxial state of stress, if stress is acting on 3 directions. Second, biaxial state of stress, if the stress is acting only in 2 directions. Uniaxial state of stress, if the stress is acting only in 1 direction. Okay. So it is the case of, this figure is representing the y-axial state of stress. This figure is representing y-axial state of stress. So in case of y-axial state of stress, if I am interested to calculate how much strain induced in the diagonal AC. Okay. So how much strain induced in the diagonal AC? So in previous class, in previous derivation, we have seen, due to the triaxial state of stress, how much strain induced in x direction, how much strain induced in y direction. We have also seen that, right? Now this is AC, this is VD, okay? So how much strain induced in x direction? If I rotate it, it is 45 degree, okay? It is clear, I hope. So y-axial state of stress, in case of y-axial state of stress, I am interested to know how much strain induced along the diagonal AC. Okay, suppose, let's simplify it. Suppose only uniaxial state of stress, okay? Uniaxial state of stress, tau. The value of the normal stress is tau. The magnitude of the normal stress is tau here, shear stress. So how much stress induced in this? How much strain induced in this? Simply we can calculate. The in which direction the load is acting, the stress is acting, is called as the longitudinal strain, and other direction is called lateral strain. So simply, what is the longitudinal strain here? The longitudinal strain will be stress by E. Simply, longitudinal strain in case of normal stress, sigma y, just we can see stress is directly proportional to strain. Stress is equal to E times strain, and strain is equal to sigma by E, and what is the value of normal stress is tau. So tau by E. That is in the x direction. Suppose you are considering this is the x direction, this is the y direction. And how much strain in the y direction? That is the lateral dimension. How much strain in the lateral dimension? So that is the epsilon x. How much strain in the y direction? Just we have seen, minus mu times longitudinal strain, and what is the value of longitudinal strain? Sigma x by E. Simply. In previous derivation, we have seen these things so many times. Okay. So this much is the stress induced in x direction, this much is the stress induced in the y direction. And now I am considering in case of biaxial. This is the case. And this is the case, this is because compressive, so it is a compressive, not the tensile one. In y direction, the stress is compressive. Please correct it. This is tensile and this is compressive, because this is compressive. Okay, this is tensile, this is compressive. If I am interested to write how much strain induced in the diagonal AC along one diagonal, any one, okay. So how much strain induced here I can write. So the strain induced is, that will be strain induced along the diagonal AC, because we are calculating along AC. So along AC we will write the longitudinal strain. And what is the longitudinal strain? Stress upon E. And what is the value of stress? Tau by E. And along the BD, perpendicular to this dimension that is perpendicular to AC is BD. And what is the value in BD direction? That is the lateral strain. And what is the value of lateral strain? Minus mu times longitudinal strain. So minus mu times longitudinal strain. What is the longitudinal strain? Tau by E. The only difference is that it is tensile, it is compressive. whenever we are writing the compressive stress, it is with negative sign. Why we are taking negative it? Because it is a compressive. Because we are considering tensile as a positive and compressive as a negative. So what is the formula here? That will be the strain along the AC is, if I am taking tau ye outside, so that become 1 plus mu. That is the case number 2. Second part of this equation. If we are combining both first and second, both are the same, strain in along diagonal AC. So we can combine both. So from first and second we can write what is the relation from first and second. From first and second, what is the relation? Tau y 2e tau y 2g is equal to, this is the tau ye 1 plus mu. So tau se tau cancel, so E is equal to 2g 1 plus mu. That is the relation between Eg and mu. So this way we can derive this relation E is equal to 2g 1 plus mu. So what is the final relation? E is equal to 2g 1 plus mu. Okay, I hope this derivation is also, so thank you very much.